We now proceed with the next topic called as non-ideal IV effects. What exactly you mean by non-ideal IV effects? These are also called as second order effects. As I've already discussed you with the characteristics, many a times I have told you the x-axis is VDS and the y-axis is IDS, and you have the characteristics like this. And you have two different color notifications. The one which you can see in black color is the ideal characteristics. So ideal characteristics is the one which it should be so. But practically, when you construct this device and try to get a version simulated graph, you find to see there is a little deviation in the characteristics from the original characteristics. Theoretically, the black color characteristics is how it should represent, but practically the characteristics tend to vary, and there you can see the difference. So what is the reason for this? The reason for the deviation in this characteristics is because of this non-ideal IV effects. Even though you take care in considering the threshold voltage to be proper depending on the doping concentrations, depending on the temperature, depending on the charge, depending on the mobility, etc., still there is a practical error which depicts the error in the form of characteristics. So what are the different non-ideal IV effects? So the different non-ideal IV effects is also called here as second order effects, and they are velocity saturation, mobility degradation, channel length modulation, body effect, leakage, subthreshold region, temperature effects, noise margin. I have not dealt it in detail. There are many representations and formulas, so only interested people can refer into this. But what you want to understand, what exactly is velocity saturation, what exactly are the different parameters here, that is being dealt in detail. So first one, what is velocity saturation? So velocity is nothing but how it is related here is velocity is the speed at which the charge carriers move. It can be the electrons or it can be the holes. So the saturation current that completely velocity saturation. So how the exactly is the relationship between the saturation current and VGS? So the saturation current increases with increasing VGS. Yes, we just now we discussed. If you look into this graph, saturation current, this is one stage with one VGS lesser value, second stage slightly VGS greater and slightly greater. So this is the representation saturation current. So saturation current, you see the saturation is attained till in this region itself, whereas here it's slightly it's different. So the saturation current increases with increasing VGS. Velocity saturation and mobility degradation are two of the effects that cause the current increase with VGS. So why is this so? The reason for this are two parameters called as velocity saturation and mobility degradation. So let us now understand what is velocity saturation and what is mobility degradation. So when carrier velocity ceases to increase linearly with field strength, so eventually as you increase, the linearity reduces and it tends to have a saturation. So very soon you will find the linearity drop and you will find the saturation. So when carrier velocity ceases, whenever the carrier velocity stops to increase linearly, that linear flow is not happening, then we call it as velocity saturation. So if you get a characteristics where the linear region is absent, so what is it you can see? You can just, it can be like this. It's not linear, it is different. It can just slightly it will go off to saturation. So that is called as saturation velocity. So we assume carrier velocity is proportional to electric field. So already I have told you V is given by mu into VDS by L, and When it is a strong field, this ceases to be true. It stops to be true. So carriers scatter here and there and velocity reaches to saturation. So whenever there is a high electric field, we have the velocity of the carriers to reach saturation. Similarly, we have mobility degradation. Mobility is given as the speed at which the electron charge carriers or hole charge carriers move. So carrier velocity divided by electric field, or in other words it is given by V by the electric field. So this is mobility given by this. As mu increases, doping concentration and temperature also have something called as channel length modulation. Change in the channel length of the transistor because of VDS is called as channel length modulation. As you apply the drain voltage, the length varies. You have seen the depletion region, whatever the region, initially this was the length, and the channel gets pinched off and the new channel length decreases as you increase the drain voltage. So that effective, the difference between the original length and the new channel is given by effective length. It is given by L minus L dash. So this is how it is created. So for long length channels, channel variation has less effects and reduction in channel length increases. So this is called as channel length modulation. You have to modulate the difference between the length. Next we have body effect. So most device is built on a substrate. So the substrate should be properly doped, but when the device is arranged in series, then the substrate voltage varies and the space charge occurs. Abruptly, charges are varied and therefore there is an abrupt variation in the body or in the substrate. So as a result, lot many effects happen. So if the substrate voltage varies, the width of the depletion also increases, and as a result more carriers are trapped there, and as a result you will see only saturation current. Therefore the substrate voltage should be applied such that it balances the structure, and as a result the threshold voltage is also normal. So gate voltage is very much necessary to invert the channel. Yes, very much true. So increase of the source voltage increases because source is connected to the channel. Therefore, increase in Vt with Vs is called as body effect. Ultimately, please try to understand, if there is any variation in the substrate voltage, lot many effects are seen. And those effects are very abrupt, and as a result the channel depletion region of the channel will vary, and as a result the same amount of carriers are trapped and you can only see a saturation current. There is no proper current flow. Or current flow you should see in three different regions: linear, cutoff, linear and saturation. You will not be able to see that. Why is it so? Because if there is any abrupt variation in the substrate voltage, the threshold voltage will vary. So increase in Vt with Vs. As the substrate voltage varies, Vt also abruptly increases. So that is called as the body effect. So in order to neutralize this effect, the body effect, that is, in order to see to it that the threshold voltage is constant, normally the substrate and the source are connected together and they are grounded. So this avoids the body effect. Leakage. So as I told you, in the substrate there are both holes as well as electrons. If you are considering a p substrate, you can see scanty electrons. If you are considering an n substrate, you can see scanty holes, but both charge carriers are present. So conduction is happening even when the transistor is in cutoff, because of this abrupt here and there charges which are present. This is called as substrate to diffusion junctions are reverse biased. So when you see the junction is formed because of the small scanty charge carriers which are in minority, they form a junction, and you can see the transistor effect and diode effects. So diode and transistor effects are merely switches and they try to conduct, and as a result in the substrate there is a current flow. So, however, reverse bias diodes do conduct leakage current. So, whether it is forward biased or reverse biased, there is a leakage current. So, this has to be avoided. So, in order to avoid this, in the substrate, we add an extra layer called as epitaxial layer. So, epitaxial layer to one extent reduces the junctions being formed and it breaks that. And as a result, leakage current is avoided. So, this few effects of second order effects can be found to minimize with certain extra fabrication or extra care during fabrication, but still they can't be completely eliminated.